Okay, we're in our V-belt drive design problem. Example 7.2, we're on step 5. Find the standard sheave diameters to achieve the velocity ratio. So these pulleys or sheaves, they come in these different standard sizes. The job now, the task at hand, is to select these sizes that give us the best ratio, the proper ratio of speed reduction. Okay, so how do we know what sizes are available? Okay, we can look for, we're working with V5 belts now, so we can look at figure 715, and that is the power rating for V belts. We're going to be using this in the next step, but anyways, we're going to use this one because it also shows us what the standard sheave pitch diameters are. These are the sizes of the sheaves that are available. They start at 7, 7.4, 7.9, all the way up here. And then these are the other sizes. Okay, so we got everything from 7 inches up to 15 here, and then 21, 27. These are the standard that are available. So the procedure here is kind of iterative. In the previous step, in step 4, we calculated what the nominal diameter of the driver sheave is supposed to be to get us in the ballpark of the 4,000 feet per minute. So now we're going to take that one step further. So the process here is iterative. You're going to choose a standard driver sheave diameter. That's the driver, that's the one that's connected to the electric motor. And it should be around 13.17 inches. And then you multiply that driver by the desired velocity ratio of 1.72. This gives the nominal driven sheave diameter. And then once you have that nominal one, you're going to choose a standard driven sheave diameter close to the nominal. Okay, and then you're going to calculate the actual VR, the actual output speed, and then the percent error. When I say percent error, is how far off is it from the 675 RPMs we want. Okay, and then based on all that, we will select the sheaves. Okay, I put a little Excel worksheet out there to help you with this. And then again, what the author did is he put this table in your textbook that shows all of these different combinations that he had tried to put together using this method to come up with this actual output speed. With the spreadsheet, and again, this is posted in Blackboard, it helps you do that. Okay, so let's take a look at the spreadsheet. Okay, so we started with the spreadsheet's protected. We started with this 4,000 feet per minute belt speed. And then we're given our velocity ratio of 1160. That's our input speed, or output 675. There's our velocity ratio. That was calculated back up in one of the previous steps. Velocity ratio was actually calculated in step 3. But here we go. Here we got it again. And then here's the 13.18. This is what we calculated in this step right here in step 4. Okay, so what happens is we found our nominal driving sheave pitch diameter is 13.18. So now I'm going to do some trials and errors. I can actually follow what's in this table here. Okay, so when I choose 13.1, for instance, okay, it gives me a driven pitch diameter of roughly 22. So when we look at 22, the next closest one is this 21.1. And then when I input that, it spits out the actual velocity ratio, it spits out the actual speed, and it spits out a percent error. And percent error is one of the things that you can use to choose, to determine whether, to which combination you're going to pick is the percent error. And then how you calculate percent error, you take the speed that was calculated with your pair, you subtract from that the speed that you want, 675 RPMs, and you divide that quantity by 675. In this case, I'm only 1% off. So in some of these cases, I can generate whatever's in this table. Let's say, for instance, we're going to start with the driving input sheave, put in the 12.4. that we ended up selecting. It tells me to go to a 21.3 is what the nominal one is, but the closest one to that is actually this 21.1. Okay, so that comes out to the 682 that they're showing in the table, and pretty close to our velocity ratio that we wanted. And when we calculate the belt speed, yeah, that's where we wanted it to. I could also try some of these different combinations. For instance, this one right here, if I tried to duplicate this 10.8, I could put 10.8 in here, and then it says I'm looking for something around 18.6. Well, the nearest sheave size to 18.6 is going to be this 21.1. So that's where we end up with this 593 and 12% error. So anyways, we went through all this. Try this spreadsheet out. It should help you. By the time we're done with this selection process, what we ended up with was we want to use this combination right here. It's a 12.4 driving sheave and a 21.1 driven sheave, and that would be the proper one. I'm going to go a couple more steps here before I break. Okay, so let's go to step 6. Find the rated power. Okay, to do that, you're going to consult this table that we're talking about here, 715, and that's for the 5V belts. If your problem is a 3V belt, you're going to look at figure 714. If it's an 8V belt, you're going to look at figure 716. But this is a 5V that we're working with, so we're going to look at figure 715. What we're going to do is we're going to consult this figure. We're going to read the rated power off of the y-axis at the point where our 12.4 diameter input sheave crosses this red 1160 RPM line. So when I come over here, this is the point I'm looking for. If I come over and read it off, I'm looking roughly 26.4 horsepower. Okay, so that's what I'm going to read here. Read 26.4 horsepower. Since this is less than our required design power of 65, we know we're going to need more than one belt. And then this design also has a relatively high velocity ratio. So let's go take a peek at figure 717, which shows us our power added. Okay, so this is a power factor that actually adds power. Just because of things like our speed ratio. Our speed ratio is relatively high at this 1.7. So if we come up this vertical line here and see where it intersects the 1160 right here at this point, we have an added power of 1.15, and that's really an added power. It's not a factor. You don't multiply it, you add it. Okay, so I take my 26.4, which I got from figure 715, and then I'm going to add to this our added power based on our velocity ratio, which is another 1.15 pounds. So therefore, we have a rated power per belt of 27.55 horsepower. That's our rated power per belt. I'm going to pick this up in the next movie. Thank you.